Estuaries to oil rigs, carbon cycling through the most productive habitats in the world. Carbon is the main element in organic compounds, so it's essential to life on Earth. It's the building block of life and energy in an ecosystem, from basic carbon filtering, aspects of light capture, to diamonds and the air we breathe. It's a fundamental core element that represents life for a lot of models. It shows the movement of energy and movement of core nutrients in an ecosystem. Carbon sequestration is a major natural method of removing carbon from our atmosphere. One of the ocean's biological pumps is the flow of carbon dioxide into the ocean surface, being fixed by the photosynthetic phytoplankton, which is then consumed by zooplankton and sequestered into the deep, dark ocean through fecal pellets or aggregates of phytoplankton detritus. But alterations to the abundance or presence of one of these vital cogs in the machine of carbon cycling will affect the whole system. That's why ecosystem-based modeling is useful in understanding the future for our waters and the influence one species' fluctuations can have on a whole system. EcoPath is a useful ecosystem model that projects a status mass balance snapshot of an ecosystem. Energy that goes in the system must be equal to the energy that comes out. EcoPath reduces key functional groups into 6 parameters: biomass, mortality, consumption, diet, fishery harvest, and ecotrophic efficiency. By estimating how much a species eat and how much they produce, we can quantify ecosystems and analyze the trophic flows of production and predation. This helps shine a light into the deep, dark, and largely unknown ocean ecosystems that we rely on for life. An example of a complex ecosystem is the estuary at Smiths Lake in New South Wales. Smiths Lake is an icol. They're common in Australia, but pretty unique globally. They're characterized by low freshwater inflow, which leads to sand barriers forming across the entrance, restricting seawater exchange. In using EcoPath to calculate the biomass of various key species to understand ecosystem function, we're able to see carbon flow through an ecosystem and whether the system is sustainable. Estuaries are one of the most productive ecosystems globally because of nutrient availability, freshwater runoff, and photosynthesis through the water column. Phytoplankton are the net primary producers in this system, like in many others, and are an essential for ecosystem functioning. Phytoplankton biomass is a key indicator for crustaceans. Crustaceans are important benthic scavengers and play a major role in the recycling of carbon through an ecosystem. They mainly feed on mollusks, seagrass, and detritus. But they're the prey of many key functional groups. Blue swimmer crab larvae are vulnerable to small fish and jellyfish. Adults are predated on by large fish and other crabs, but their main threat is humans. A study done in 2010 in Chesapeake Bay in the US found a stock assessment where crab stocks were extremely low and steadily declining with overfishing and restricted recruitment into the estuary. Biomass of crustaceans has dropped dramatically, from 3.69 to 0.006 grams per meter squared of biomass in Smiths Lake in 2020. As you can see in these very basic graphs, the abundance of crustaceans is extremely low in relation to the ecosystem. If we assume zoobenthos makes up 50% of a crustacean's diet, the biomass of zoobenthos is an order of 100 times smaller than needed to support its predation. If we look at jellyfish, the biomass has skyrocketed since 2017, at 50 grams per meter squared in 2020. Jellyfish are placing extreme pressure on crab larvae and nutrient uptake. Due to the abundance of jellyfish, crustacean biomass in Smiths Lake has dropped. A paper done by Pauly in 2009 studied an estuary to outline the direct relationship between jellyfish and phytoplankton abundance, and the trophic cascades jellyfish can cause when present in an ecosystem. But why are there no crabs? Additional to predation and fishing pressure, Smiths Lake has been closed for the past 18 months, so recruitment and growth are limited and mortality is the only remaining constant. EcoPath is useful to show the imbalances in Smiths Lake ecosystem, some quantitative data, and an easy method of understanding ecosystem dynamics. It does have its issues though. It's only a static mass balance ecosystem model, only a snapshot of time. There were also issues in collecting some data, and the model relied heavily upon data from previous years that may not be relevant now. The crab biomass was also calculated from data we found in literature, not raw data from the lake. Biomass also isn't a perfect representation of ecosystem function. Jellyfish are less dense than fish, so weren't included in models for many years, but they exert extreme pressure on ecosystems. Water parameters should also be more prominent in ecopath studies. The study of Chesapeake Bay found with ecopath that water parameters affected blue crab's biomass and could be enhanced with reduced nutrient input. Crustaceans are vital in aiding nutrient and carbon flow and uptake in a system like a natural estuary. More jellyfish and enhanced fishing pressure, less zoobenthos, and more small fish would mean less crabs, less uptake and sequestration of carbon, altered nutrient flow, warmer waters, and necessity for ecosystem modeling. It's possible our future waters will need to be heavily facilitated artificially due to habitat destruction and climate change. We can see this in the possibility of artificial reefs, like one developed around a decommissioned oil rig in California. A study was done in 2014 on an oil rig off the coast of California and found the ecosystem had the highest secondary production rate of any studied ecosystem globally, related to the ratio of high substrate to sea floor and protection from larval and juvenile pelagic fish. Rockfish species have the highest biomass in the system and feed primarily on small crustaceans and fish. Their main threat is humans, as a study of rockfish in California found 87% of species in California waters were commercially fished. Oil rig habitats also have a high value, partly in terms of fishing. They're also more accessible to pelagic fish in the upper 100 meters of the water column, and the recruitment production per square meter is 3.7 times that of a natural reef. You can see here that the oil rig reef is the most productive, followed by many estuaries, both extremely important habitats for global carbon cycling. Using modeling, the study found the reef to have a high total annual production, between 100 and 900 grams per meter squared of biomass, but it had a low biomass flux. The flux is the total biomass of a species that visits the reef at any given point in a year, but shows a small ratio, which means a large abundance of associated visitor species and the reef's susceptibility to overfishing. High production rates means enhanced cycling of carbon and nutrients through an ecosystem, which allows energy to flow through a greater number of trophic levels. Ecopathic modeling is necessary for management of fishing and understanding biomass flux. Limited secondary production would mean static trophic relationships and a limited energy flow. This has implications for inevitable decommissioning of over 7,500 oil and gas platforms. Should they all become artificial reefs? Will that promote production or attraction? Will people abuse it to overfish? All questions for future ecopath and ecosim. Overall, Smith's Lake and the oil rig reef are both robust ecosystems. Smith's Lake is being pushed to its brink. Through ecopath, you can see that it is currently unsustainable, and although there are human errors with sampling, the high abundance of jellyfish and low abundance of crustaceans have negative implications for carbon cycling and trophic dynamics in this system. Overfishing, a closed lake, and favorable water parameters for predators impacts crustaceans' recruitment and abundance. The estuary surface doesn't change much, but below the surface, the ecosystem is changing, every day, every week, every year. The only way to see that is through ecopath. The oil rig reef has the potential for future prospects for ecosystem management. We could rely upon artificial structures if natural ecosystems experience trophic cascades. In order to achieve this, we need to use ecosystem modeling techniques like ecopath to understand ecosystem function and sustainability, management to protect areas from overfishing, inform research policy, and predict the response to alterations in carbon and nutrient uptake. Ecopath is the means by which we can see these complex interactions of organisms in an ecosystem in ones and zeros. It's a limited attempt at understanding how life flows through an ecosystem, but it could be the light we need to see into the dark future of our world.